Greetings my fellow gamers. Grass is an important part of video games. It is one of those things that is rarely paid attention to when it's done right, but do it wrong and everyone will notice. It's not helped that most people don't realize just how deceptively complicated this topic is. While rendering something like a single piece of grass isn't much of a deal, the performance cost quickly goes through the roof as we try to render thousands or even millions of blades. So how do video games render countless blades of grass? What tricks do they use to save your PC from exploding? And how can you, yes you my dear viewer, use literally the same tricks as games like Death Stranding or Ghost of Tsushima to create realistic looking grass and optimize your game? Well, keep watching and you'll find out. Okay, so before starting any project, it's good to have at least a rough plan of what to do. In our case, everything is straightforward. We need a grass model to render and a bunch of positions where it should be placed. When choosing a model for a grass, there are generally a couple options. For now, I'm going to use a technique known as grass cards. The idea is to take a bunch of textured quads and intersect them at different angles, which creates an illusion of a lush grass. It's actually the same technique used in games like Death Stranding and Apex Legends, mainly due to its simplicity and high performance, as the bulk of the work is done by a texture. For my scene, I chose the following arrangement of 3 quads with a grass texture from Minecraft. Now that the prefab is ready, all that's left is to generate the positions and instantiate it. I define a variable for my grass field resolution and use it to loop over grass X and Z positions. In order to center the field, I will subtract half the resolution and then add 0.5. All that's left is to click play and... Yeah, you could say our field has a couple issues. First of all, we have a small stutter in the beginning. It doesn't seem like an issue now, but remember, we're currently rendering only 22,500 grass prefabs and the growth of our field is exponential. But generating positions isn't even the main issue. I mean, sure, it will become a bottleneck sometime in the future, but we need to generate them only once, plus PC gamers are already used to waiting ages for shaders to compile. No, the real question is, what's with that FPS? 32 frames? This is nowhere close to the stable 60 FPS that Ghost of Tsushima has, and the grass there is fully 3D, as well as, you know, it has a game attached to it. You see, all our problems stem from this single line of code. Because as it turns out, instantiation is really fucking bad. Currently, when we tell our CPU to display our field, it sends data to the GPU, then waits for it to process each grass prefab individually, and then sends all of the data back to the CPU. The CPU then executes a shader on each blade of grass, again individually, which sends the data back to the GPU to process. Finally, the CPU gets the response from GPU, shows us grass, and then deletes all of it! Then it starts the entire loop again, shows us the result, and then deletes it. Then it starts the loop again, shows us the result. I hope you see where I'm going. For your information, sending huge amount of data between CPU and GPU is a big no-no in graphics programming land. It's extremely slow and stops the execution of the CPU thread until all the data is done sending, hence the stutter. Luckily for us, we can fix both these stutters and low FPS by utilizing compute shaders and a technique called GPU instancing. As mentioned before, regular shaders are firstly executed on the CPU, which then sends the data to the GPU to process. On the other hand, compute shaders are executed entirely on the GPU, meaning they're super fast and avoid sending data to the CPU unless we explicitly tell them to. If you wanna better understand them, go watch this video, I will put the link in the description, but essentially we divide our work into threads, send all of the relevant data to the GPU and then dispatch a compute shader that performs some calculation. However, it still doesn't solve the issue of us drawing each of our grass blades individually, even though all of them use the same models. This is where GPU instancing comes into place. Using it, we send our model to the GPU once and then tell it to store it in its local memory. Now when we render our grass field, it will be done using the same model with one giant dispatch call. The result is a beautiful field of grass at around 420 FPS, so let's expand it some more. I personally made it 300 by 300, which is good enough for now. Okay, enough with the nerd shit, it's time to make stuff look pretty. I started off by adding a density modifier because currently the grass is spaced too sparsely. It acts as a multiplier to grass resolution, while on the compute side we divide the grass position by it. To make it easier to visualize, let's take our 300 by 300 field as an example. With a density of 2, it actually becomes a 600 by 600 field. After passing it to compute shader and centering, it will be in the range of -300 to 300. Finally, we divide it by density, which results in a final range of -150 to 𝓈𝓊𝒷𝒾𝒷𝒾𝒃𝑔. Speaking about position, it looks too uniform. Grass in real life tends to be more randomized. To fix it, I used a compute shader noise implementation that 𝓈𝓊𝒷𝒾𝒃𝒃𝒃 used, because if I'm going to steal a video idea, I might as well steal the noise library. Anyways, while the positions are now pleasantly randomized, the grass height isn't, which looks strange. Luckily for us, compute buffers can hold many types of data at the same time, so I refactored my buffer to hold grass height displacement. The calculation itself is fairly simple. We just specify the UV, sample the height map, which looks like this, and then take the luminance as our value. Grass position is used as an offset for the vertices, while normalized displacement is used to calculate the final height displacement and to animate the grass. For the fragment shader, I kept it fairly simple as well. I use my texture as the main color and interpolated with black at the bottom to simulate ambient occlusion. Then, in order to simulate young and old grass, I add tip color that is based on normalized displacement. Here's the result. Our grass is essentially complete, however we still can squeeze some more performance using optimization techniques. I'm actually planning to make a dedicated video on this topic, so if you aren't interested in this shortened version, you can skip to the next section. Anyways, let's get started. The most basic optimization that we can do is called distance scaling. The idea is to define the max distance at which our grass will be displayed. We then compare distance from our camera to the grass position, and if it's more than that, then we don't draw, or in other words, scale it. Another type of culling that I wanna discuss is frustum culling. Like films that can send everything that they wanna render to a data farm, video games have to use limited graphical resources of a single GPU. Thus, it would be a good idea to only show the things that a player can actually see. That's right guys, in game development, object permanence is a lie. Everything phases in and out of existence when not in direct view. Anyways, that's where frustum culling comes into place. In order to display a 3D object on your 2D screen, the graphics pipeline goes through several matrices that transform the vertex into several different coordinate systems. One of the coordinate systems that we go through is called normalized device coordinates, or NDC for short. Unlike UVs that range from 0 to 1, NDC go from -1 to 1, with the center of the screen being at 0. Everything outside this range is essentially unseen by the camera, so we can use it to our advantage and not display the grass that the player can't possibly see. I also want to mention that the order that we are doing our culling matters, so the less expensive ones should go first. The final trick I will show you today is called level of detail, or LOD for short. The idea is similar to distance culling. We define some distance value, but instead of using it to cull grass blades, we will use it to decrease the quality of faraway grass. After some adjustments to code, here's the result. Comparing it to the original version, the visual is essentially the same, while the performance is significantly improved. However, a new problem arises. At distance we only get one grass quad, which, when viewed from a wrong angle, easily breaks the illusion of our field. A simple solution is to make this quad rotate to always face the camera, using a rotation matrix. Again, if you don't know what a matrix is, don't worry, I will explain it in the future. This technique is called billboarding, and it is actually the second option for a grass model that you can choose for your field. If it looks familiar, you are not mistaken, as it is the same technique that Doom uses to try and make 2D sprites look like 3D objects. It is incredibly performative and is still used to this day to display things like particles of fire. But the caveat, of course, is that the illusion breaks if you come too close, so I'm keeping it at a distance. Our grass field is essentially complete. On my PC it runs at 230 plus FPS, which I think is a good enough result without delving into more complex GPU-based optimizations. I must say though that despite being performative as it is, our grass system has its issues. As mentioned before, all the work of generating and rendering grass is done on the GPU, which means that as far as our CPU concerns, the grass doesn't exist. This means we have no collision detection and no optimization algorithm for our grass unless we ourselves implement them, hence the section where I did optimization. Additionally, unlike CPU shaders that run calculations sequentially, GPU shaders run them in parallel in the thread group. While this makes them really fast, it also makes them prone to bottlenecks, as the execution of a thread group will not finish until all threads are done with the calculation. Basically, the thread group is only as fast as its slowest thread. As far as I'm concerned, this is a fair trade-off, but it is something that you should be aware of nonetheless. Anyways, thanks for watching, and if you like the video, consider subscribing to the channel and or my Twitter. That's all for today, peace.